Okay, welcome back, everybody. Hope everyone had a good week. Just a couple of quick announcements. One, I sent an email concerning the question of the day that exams are given. It wasn't updated, but the exams, FYI, is I give them on Saturday. Okay, meaning they're available for you on Saturday. Quite a time period, actually, because I open it up at midnight, which is technically Friday night, midnight, really, right after midnight, minute or so after. And then it closes midnight on Saturday. So you have all that time period to finish up the chapter, the exam. And I picked Saturday because that tends to be based on experience with respect to the last few semesters of where students are in work and family issues. That tends to work pretty good. If it doesn't work for you, let me know. I could extend it maybe to open up on Friday, and that's a better schedule, but we'll see how it goes. All right. Any questions? Everybody know where they need to go as far as on the Canvas course and where they need to get information and so forth. A reminder, if you need assistance, you need help tutoring, get it, you get it on campus. You can set up a meeting with me between 3 and 4 on Tuesday and Thursdays. And if you want to hear more of the topics we talk about, you're more than welcome to come to my lectures on Tuesday and Thursday, 1 o'clock and at 4:15. Okay, same link. All right. Any questions, comments, concerns? If not, I'm going to continue with chapter 1. We're in slide 22, based on my notes. And then we'll get into chapter 2, possibly start chapter 3. Now, probably what's going to happen, I know we have next week scheduled for the first exam covering chapters 1 through 3. More than likely, I'm going to move it to the following Saturday because I don't want to give you one day. If we don't finish chapter 3 today, then we'll finish it next Friday. And I don't want to give you just one day to prepare for it. So more than likely, we'll shift it over. And generally, the first exam is like that. Chapters 1 to 3 is quite a bit of information and so forth. After that, it kind of spreads out fairly evenly. So we'll see how it goes, but I'm pretty sure I'll do that. Which reminds me, good question was asked me was I have all the assignments, like for example, homeworks 1, 2, and 3 due the day before the exam. Okay. Now what I've done, I just grouped them in that area. Obviously, some of the chapters are going to finish way ahead. Don't hesitate to, just because they're due on, next week, not to do. Okay. The homework, you have 2 attempts. I mentioned before, I believe, that a lot of students attempt the first attempt just to get a ballpark, get an idea where they're at with respect to that chapter. And then after the chapter is done, complete the second one. Okay. Unless you're happy with the first grade. Because I won't make any homework due until we are done with that chapter. So I will move chapters, accordingly and depending on where we're at. But again, I just put them all together before the exam. But don't wait till the night before to do the homework. So no, keep on top of it. All right. I believe that's all I had. No hair. All right. If there not any questions, we will continue. And where we ended up with was slide 22, based on my notes. We had just finished talking about, or began talking about this chemical process. This is a chemical change. Okay. We were talking about physical changes and chemical change. And the difference is this. The physical change, the chemical structure, the chemical formula does not change before and after whatever you do to it. Okay. H2O as ice is H2O as vapor. Unlike a chemical change where the chemical literally gets converted to something else. It is a totally different compound. Here we have a chemical equation, okay, which we normally write as follows. We have the arrow, which should indicate I got some type of a process, either a chemical process or a physical process. What are in front of the arrows are what we call the reactants. Those are the two, or maybe the single material is whatever it is that's something's gonna happen to it. And then it undergoes a process, and then we have on the right side the products. Okay. So here we have sodium metal, which is in the elemental form. You can see the picture of it here. It's a metallic. Okay. It is a very soft metal. It is very reactive, extremely reactive. It's in fact, when we use this, we actually have to store it in an oil, because storing it in the air, open to the air, storing it, you can't even store it in water because it's very reactive. It reacts violently with water to produce a lot of heat and hydrogen gas. And that heat ignites the hydrogen, so you get a nice little boom. Okay. And then over here, this yellow colored material is chlorine. Okay, chlorine. And in this reaction is chlorine gas. Chlorine is a very poisonous gas, extremely poisonous. I have mentioned in the past that chlorine is utilized by a lot of municipalities where they treat water treatment plants to get rid of bacteria, because it's very effective, very inexpensive, but it's very poisonous. And so if you ever see a cloud of this material, if you're near a municipality and you see a cloud of yellow cloud, almost a greenish tinge material up in the air, get upwind quickly, because you have a terrible gas. So we have a very poisonous reactive, fairly reactive gas, very reactive metal. They combine and they form this species here, denoted by the formula of NaCl. Now, in this formation, sodium is no longer elemental sodium. It is now what we call ionic sodium. Much more on that later on. Chlorine, this is the name of the element. Chlorine gets converted to now what we call chloride. Okay? And this is what we can put on French fries, sodium chloride. Very, not as hazardous as sodium and chlorine. And the only difference, the only thing that happened here, which to me is, it kind of really got me going with chemistry, was two electron transfers between the sodium and into the chlorine. Okay, 2 electrons, extremely tiny chunks of matter, totally changes the property of the chemical. So, classic example here of a chemical reaction. All right, so now you may be given choices here. You're given chemical equations or physical equations. We don't know which one it is. And you may not know what the chemical is, and that's okay. But you have the power of deductive thinking, okay? And that you can look at the formula that is given in the reactant side and then look at the products. And you're given the same formula before and after. Guess what? You got a physical change. If the formula no longer is the same, you must have a chemical change. Okay, so let's walk through one of these. Now, obviously, right now, you may not know what this is. I'll tell you when we're done, but we have this chemical, which has a nitrogen and 3 hydrogens attached to it. Okay. 99% of the time when we write formulas, the first element that we write is generally what we call the central atom. And then whatever follows is bonded to the central atom. So we have nitrogen bonded to 3 hydrogens around it. And we're going to learn more about this guy down the road here. So next thing we know is that is in the gas phase, its physical states in the gas. We have the process here, so we go look at the reactant side, and lo and behold, guess what? The formula literally has not changed, okay? So that in itself should tell you, I have a physical change occurring here. And then to verify that, you look at the physical state of the product. It's the letter L, which means it's a liquid. So we went from a gas to a liquid, which we call condensation. Remember that? Okay. All right. Number two, we have the same formula again, nitrogen bonded to three hydrogens. And then we have a coefficient in front of the NH3. That coefficient up front is telling you how many molecules, how many of these compounds are there, and it's telling you there's two of them. Okay, much different than the subscripts. The subscripts tell us how many atoms are within the structure of the compound, and that doesn't change. Once we determine what that subscript is, that is etched in stone. That's the formula. The coefficient, the big number in front, we can change any number of times. We can add, make it 3, make it 4, if we need to. Okay, we'll learn more about that. Okay, so now we got a process occurring, and guess what? We have on the reactant side a plus symbol. That is a flag for you to tell you, you know what? I have a chemical change because now I have two different products. In this case, I have nitrogen, okay, and I have hydrogen. Totally broke the NH3 apart to break it apart to produce the elements that were used to make it. Okay, and so we have a chemical process here, okay? Because the NH3 has been changed chemically to produce N2 and H2. Now you may be wondering here about these subscripts for like H2 and N2, and we had previously Cl2. Okay, we're going to learn that there are 7 elements in the periodic table. There are 7 out of the 18 elements that do not exist by themselves. Most of them, the other 111 elements by themselves, that's how they exist. Okay, these 7 do not, because from a energy perspective, it's a very unstable state to exist by themselves, at least here on Earth at 25 degrees and 1 atmosphere. So what they do is they combine with another element of itself to form what we call diatomic elements. And there's 7 of them. We're going to learn which ones they are. We've been introducing here chlorine so far into H2. We also introduced O2, oxygen. Okay, and that 2 are just telling us two atoms of hydrogen bonded together. Okay. All right, so now we have, let me clear it up a little bit, get rid of some of this mess here. Now we have another species here, number 3. So we have a physical change here. We've had a chemical change. We're going to go through each one systematic. I advocate always using a systematic approach when attacking the problems. Eventually, when you become proficient and become knowledgeable about how these the approach is, you can shortcut it and produce your method of how you want to attack the problem. Okay. All right. So here we have something with a H2O2. At first glance, you would think H2O, but notice that H2O is not equal, does not equal to H2O2. Obviously, you can see that, right? There are 2 hydrogens and 2 oxygens in this structure. And I'll explain what this is, but I'm sure you're familiar with this. If you ever cut your finger or even use it to dye your hair, you use some of this chemical, H2O2. Okay? So here we have it in liquid form, and then again we look at the process, look at the products, and again we have the plus symbol, which again gives you a flag. I got 2 products, specifically hydrogen and oxygen. So here, as in the case of number 2, I have a chemical change because I have totally changed the chemical structure of my reactant. Number 4, we get the same chemical again in liquid form. Okay. We look at the arrow, we look to the right of the arrow, and guess what? We have the same formula again. So that in itself tells you I got a physical change. Okay, because I did not change the formula of the product. And I go and verify that with respect to its physical state. It's a liquid and then becomes a solid. So I'm freezing it. It goes from liquid to a solid. So that's definitely a physical state. Okay, this last one again, you don't know what it is. That's okay. But you can see I got 6 carbons and 6 hydrogens in this formula for this compound, which because I only have carbon and hydrogen, this is an example of general term called hydrocarbons. Hydrocarbons are compounds, specifically organic compounds, that are made up of nothing but carbon and hydrogen. We utilize a lot of hydrocarbons when we're driving our vehicle. All right, so then we look at the reactant site and guess again here, like the others that demonstrated a physical change, nothing's happened to the formula. We still have C6H6 in the reactant site, product side, excuse me. And so we checked the physical state. It went from a liquid to gas, which is boiling or evaporation. Okay. And so what we did here is not only what the chemicals are, okay, which really doesn't make a difference here in trying to answer this question, because all they want to know is that reaction, that process is indicated, is it a physical or a chemical change? That's all they're asking here. Okay. So there you go. Now to tell you what they are, because we're going to be using this one for sure, that one's called ammonia. NH3 is ammonia. That's the formula for ammonia. The one I said that you may have used if you ever cut your finger, well, that is hydrogen peroxide. Okay. Or, some people use it because it does react with your hair and kind of blondes you up a little bit. Okay. So, and then, the last one, actually, the last one is C6H6, the hydrocarbon. That one, that's the formula for something called benzene. Benzene. The actual name is not important right now. This is beyond the scope of Chem 130, but I'm just giving it to you anyway. How it come out? Benzene, I can't even spell. E. Zoom and my pen are not doing well. My digital pen works fine with other applications. For some reason, Zoom, it's not. I gotta question out their tech support with Zoom, and I get to hear from them to figure out what's going on. I can't draw as fast as I used to. All right, so benzene, hydrocarbon, it actually is a cancer-causing agent too. So very not a good chemical. Okay, so let's talk about elements, compounds, and mixtures. Okay, with respect to elements, that is what elements are made up of one type of atoms. Okay, they could be single atoms like He helium here, or they could be what we just talked about, diatomic elements. And they are diatomic because they're unstable by themselves. Okay. Now, the element itself, we can't break it down to anything else. I mean, we can take, for example, H2O, water, and we can go hydrolysis and actually break it down to the elements of hydrogen and oxygen. Okay. So compounds can be broken down back to the elements, but the elements themselves, that's it. We can't go any further. If we break them down, we start breaking them down to the subatomic particles. It's a totally different ballgame. Okay. Compounds, by definition, a compound is made up of 2 or more, at the minimum, 2 or more different elements. Okay, 2 or more different elements. The diatomic H2 is made up of 2 of the same element, so it's not a compound. Okay, whereas say H2O is made up of hydrogen and oxygen, 2 different compounds, right? 2 different elements, excuse me. So this is a compound. Okay, this is an element. Now, what happens, the term molecule, you may see it in your textbooks. A molecule is generally used to describe a molecule, a diatomic element. So a molecule of hydrogen, but it's interchanged with other compounds. You may see it being used for a molecule of water, H2O. So a molecule is just telling you one compound or element, okay? Nothing special about the term molecule. And then obviously, pure substance material is just made up of a particular material, whatever that material is, okay? And a mixture, stands for itself. A mixture is two or more different compounds or different elements or any combination of elements and compounds. Now, this is a kind of a diagram to kind of break it down for you. If you look over here, here's matter. And we come on here to a mixture. And the way they're drawn here, they're drawn with these circles with different colors to designate different elements. So you see the dark ones here, that would suggest that we have an element. Now look at the ones that are together. That would suggest that it's a diatomic, obviously, right? There's two of them put together, diatomic. Now, the fact that those two are the same color, and the two red ones are the same color, would tell you those are elements, diatomic elements, all right? And that this one on the left would be a mixture of two different elements. One happens to be a diatomic element. Compared to the right, we got the, I guess, greenish color ones that definitely they're all by themselves, suggest an element. And we got the red ones by themselves, and then the dark ones by themselves. So we got a mixture of at least three different elements. Now, with respect to compounds, they must be made up of two or more different elements. So we have this model here where we got the dark red and the two yellows, like Mickey Mouse, right? Mickey Mouse ears. We got the red in the middle, and then bonded to that are the two yellow colored material. This could be water. That's a good model for water, where the yellow ones, the little small ones, are the hydrogens, and then the red center is the oxygen. Well, that's a good example of a compound. Okay, and if you draw these, if you have an assignment where you got to draw a compound, make sure you show the distinct difference between if they're the same shape, size, and roundness, and you're trying to describe a compound, then make color one in or something so you can distinguish the difference. Because if you put them together as two circles, then all you have is a diatomic, as compared with two circles where maybe you color one in, now you have a compound. Okay, all right. Like the case here with this one, where you have sodium chloride. And then elements themselves, and then this side, these are diatomic. A good example is oxygen or any of the diatomics. The point being that the two are the same shape, colors, the two spheres are the same size, same color. And then we have the ones that are single all by themselves, it's single element. Okay. Right. We tend to use a lot of diagrams to show things. So yeah, be prepared for a lot of diagrams. All right, so examples of mixtures, for example, metal alloys is a very good example. The ring on your finger or whatever jewelry you're using, gold jewelry, is not pure gold. It is an alloy. It could be 18 karat gold, 24 karat gold. The difference is that pure gold in itself is very soft and doesn't lend itself very well to being made into jewelry. So they add another element into another metal to give it a little strength. Like brass, for example, is a mixture of copper and the zinc. And steel is not pure iron. Stainless steel, I should say, is not pure iron. It is made up of things like carbon, and they add some other elements in there, metal elements, to give it the strength. Because pure iron would not lend itself well to being used to make structures because it's, not very sturdy. Sand, granite, tap water obviously is a mixture. We just loaded with all kinds of stuff in tap water, all kinds of ions, electrolytes, what we're going to learn about, sodium chloride and so forth, and all kinds of other organic material. And the air around us is another example because we get a variety of gases around us. Okay, so some examples. Things like pure material, obviously you had table salt after you clean it up, you got nothing but sodium and chloride compound. Diamond is made up of carbon, and if it's a pure diamond ring, for example, with no other material in there, then that's a pure material. Obviously, that's rarity, having pure 100% diamond. But the takeaway from the diamond is this: diamonds are made up of carbon. Okay. There are materials out here, like they're called dry lubricants, like graphite, where they're very slimy filled. Okay. They're a dry lubricant. They're used for lubrication and not, not like oil, but lend itself to act like oil to allow something to gears to move better or something. It's metal contact. But the point is, well, they're both made of carbon. And yet, diamonds made up of carbon are the hardest thing on Earth that we know. As compared to graphite, well, obviously it's not. They're not the hardest thing. But from the atomic scale, it's still carbon on both sides. And you tend to think, well, why? And that's because the structure of the carbon atoms is placed in such a manner that it makes it, when it's put in the diamond structure mode, it makes for a very hard material. If it's put in a different mode, it makes for a if you put it like in sheets, carbon sheets, it's very slimy. Okay. So structure has a big factor in how the atoms interact with each other. These intramolecular forces have a big effect on the overall aspect of the material. Distilled water, unlike tap water here, 99.9-ish, there's always some material that always comes across, but distilled water is nothing more than, you take the water and you boil it, you run it through some condensers and collect it someplace else to get it clean. Okay. And some of the elements themselves are like mercury is pretty pure. All right, the diagrams I was talking about, well, we use things as diagrams as follows. So if you are going to present any type of diagram, make sure that you're very distinct in describing, like I said earlier, difference in color. Because you can see in this example here, they're about the same shape. And if I were to just submit something that looked like this, well, that could be an element. There are some elements that have multiples of each other than diatomic. So make sure you make one distinguishable like that. And that would be a good example of a carbon. Okay. This is a good example of a diatomic element. Okay. And obviously we got a mixture here. So we got a mixture of an element. Denoted by that, a mixture of a compound because it's made up of two more different elements. And then we got a second type of element. So we got three things going on here, two elements in a compound. Okay. So if you upload a file, you want to show your elements, make sure you label them so describing what you're describing. I see a lot of diagrams get uploaded and I don't know what's what, and it's just thrown around all over the place. Okay. So again, always think about when I write something, okay, or when I draw something, present something, put it in the manner so a year from now, if you want, you look at it and you know exactly what you wrote. You won't be like, I don't remember what I did here. Okay. All right. So here we have, you may have some diagrams and you're being asked, okay, what do we have here? Well, A, for example, is definitely an element, right? We've seen quite a number of examples of that, specifically a diatomic element, okay? B, we have a dark circle and three smaller white ones would actually indicate a compound, okay? That could be a structure for ammonia for you, where you got the nitrogen in the middle and the three hydrogens bonded around the nitrogen. The C is definitely, we have elements, okay? But it's a mixture, specifically a mixture of two different elements. And D, nothing but the dark circles would indicate, okay, that's a model of a diagram of an element. E, as in the case of B, two different elements denoted by their different colors and shape, okay? And then again, F is a good example of a mixture where we have two compounds and a diatomic element, okay? And then G, we have an element and then a compound mixture. And then H, obviously, they're all the same, and even a more descriptive name would be a element. Specifically, looks like a solid because everything's nice and ordered. Okay. All right, so you might come across diagrams of salt or be asked to create diagrams of element, compound, or a mixture. All right, let's change a little bit. Let's talk briefly about elements. We're going to talk in more detail down the road here, but it's kind of introduction. Okay, so every element has its unique name and unique symbol and unique number. Let me share the periodic table, which I have marked up with other things, and which will become clear in a minute. Not in a minute, but down the road here. Okay, but you can see there's 118. Now, if you look at the elements, 115, 116, 117, 118, those elements have been discovered, obviously, and have been given a name. So this periodic table has not been updated. In fact, I want to say 115, 116, 118 are only about 2 years old. Okay. Now, if you look at the trend here, as you go across the periodic table, we start with number 1, which is hydrogen, upper left corner. And then we shoot across number 2 to helium. Then we go back to the next row with lithium. Okay, notice I got a number sitting there too. Okay. And so with that trend, look at number 18, bottom right corner. Okay. Now, if they were going to, and they are working on it, if they were to discover element number 119, can you predict what position it would go? Where would it be? Where would I put it on the periodic table? What is your deductive reasoning guide? Given the trend you see in the previous elements, going from left to right, where would you say number 119 would go? Or can I make a prediction? Sure you can. Okay. Any ideas? Anybody there? Right, it would go into number 8 over here, and number 119 would go right here, based on the history of the other elements, and we'll continue a whole new row. Right, below 87, correct, Grace. And then we'll shoot across the periodic table. And like I stated, they are working on them. There are scientists that's their sole function in life is to create elements. Unfortunately, a lot of these elements are not very stable. They're radioactive. They don't survive very long, but nevertheless, they're working on them. All right, trying to find them, get them. So each one has their own unique name, their own symbol, and their number. Okay, I'm sorry, I thought I mentioned the number up here, but let's go back to it very quickly. You can see carbon over here. It has its own symbol. Uppercase C has its own number, number 6, and it has a decimal number underneath the letter. That is the atomic weight, okay? If you go to anyone, here's oxygen, okay? It has its own number, because it starts from 1 over here, and then 2 over here, and then we go back to 3, 4, etc., and then go left to right, okay? And then the bottom is what we call the atomic weight for that, or yeah, the atomic weight. There's another name that is used interchangeably, but we'll get to that. All right, so having their own, they all have their own symbol. A lot of them have one letter, okay, as a symbol, and that one letter is capitalized, always capitalized. Okay, if they have a second letter, then that second letter is always lowercase. It is very important, because if you're not careful, and if you are wanting to designate, talk about cobalt, which has a symbol capital C lowercase o here in here, and you inadvertently write it with both capital letters, then what you have done is given the formula for carbon monoxide. Okay, so we have to be very, very specific. You have to be very careful. So make sure that second letter, if you are talking about an element with 2 letters, make sure that second letter is lowercase. All right, so most of the elements have English names. H for hydrogen, O for oxygen, and then He for helium. A lot of them do have are derived from Latin names. For example, the symbol for lead is Pb, which comes from Latin, coming from the term plumbum, which means waterworks. Okay, and then gold has a symbol Au, coming from oleum, which means the golden dime. Now, be familiar with the first 20. And what I'm going to do is very quickly go through the first 20. And we would start with, change the color here. Start with the upper left one, hydrogen. Okay, H for hydrogen. Okay. Then we shoot across for He for helium. Then we come back to number 3, which is Li, lowercase I, lithium. Next to it is beryllium. Okay. B is for boron. C is for carbon. N is for nitrogen. O is for oxygen. F is for fluorine. Notice I'm saying fluorine, I-N-E, not fluoride. Okay. If you have fluorinated toothpaste, you are brushing your teeth with fluoride, not fluorine. And it'll become clearer in a bit why the difference of the naming. Then we had number 10 called Ne for neon. Number 11, we go back to the number row number 3, which I got the number there. Na for natrium, which means sodium. Then we have Mg for magnesium. Good old L, number 13 here, aluminum. Si, silicon. P for phosphorus. S for sulfur. Cl, note the name, chlorine, chloride, chlorine. Ar for argon. And then we go back to row number 4. And we start with K for potassium. Okay, number 18. And then number 20, Ca for calcium. Okay, now the element calcium, there's 2 types of calcium. There's the element calcium, and then there's the calcium utilized in your diet, in your bone structure. Totally different. Okay, the difference between the element and the calcium in your body is 2 electrons, 2 little tiny electrons. All right. Note something too on this periodic table. on the very top of each column, you have the Roman numeral 1A. For that one, the next one is Roman numeral 2A. Then we shoot across to boron. You got Roman numeral 3A, 4A, 5A, 6A, 7A, and then 8A. 8, the number 8 is very significant with respect to stability of the atoms. The driving force, put this in long-term memory, the driving force for any chemical reaction is to get to that magical 8 with respect to electrons. To have 8 electrons around what's called the outermost shell. We'll learn that these electrons are in different energy levels. And the outermost shell that's where the actions happen. That's where all the chemical processes are occurring. And what's happening here is elements either are going to gain electrons to fill the outermost shell to that magical 8, or they're going to lose electrons. So the next layer in has 8 electrons around it. Those electrons in the outermost shell have a special name. Those are called valence electrons. Valence electrons. A lot more on that. That's just an intro to that. And we can determine the number of valence electrons for those A elements by simply finding them on the periodic table and looking at that Roman numeral they're telling you. Okay. So on top of the 20, also be familiar with Ag, which is silver, then Au, which is gold, Pb, lead, Br, bromine, okay, I for iodine, Cl, remember, for chlorine, and F for fluorine, remember those? Okay, and then the last one, mercury, with the symbol Ag, okay? All right, now, we're going to talk about the physical states of these elements. We're going to have a periodic table here to help you out so that any of the 118 elements that we have, you can say, okay, that element is either a gas, a liquid, okay? I had a senior moment there. It's either a solid, a liquid, or a gas, okay? Because under standard normal conditions, meaning 25 degrees Celsius, which is about room temperature, and in 1 atmosphere, we are in 1 atmosphere here, at least down here in Santan. I don't know what they're, I'm just kidding. Well, all around us is about 1 atmosphere. Go up to Colorado, slightly different, much less, okay, a little bit less. Now, under these conditions, there's 118 elements, like I stated. Two of them are liquids at 25 degrees, specifically the metal mercury and bromine, okay? Now, there are 12 that are gases. Okay, so we have hydrogen, nitrogen, O2, oxygen, fluorine, chlorine, and then these noble gases. All right, I'll show you the periodic table here in a second. But notice earlier I said Roman numeral number 8, VIIIA, that is the last column of the periodic table. Those guys are called noble gases. And the reason they're called noble gases is because those guys are very inert, very unreactive. And the reason they're unreactive is because they have that magical 8 electrons in the outermost shell. The only exception is helium, which has its magical number is 2, okay? All right, so there's 12 gases, and then everybody else is a solid. Okay, so let's go through the table here. So everybody here in yellow are the gases. Now, these are the noble gases we were talking about. Change the color here, right here. Roman numeral 8A. Noble gases, very unreactive because there's 8 valence electrons on the outermost shell, with the exception of helium, where its magical number is 2. The rest of them, 8. And the driving force, as I said earlier, is to get to that 8. All right. Don't forget hydrogen over here in the far left. It is not a, first of all, it's a gas, okay? And it's not, we put it there for a reason, soon to know why. Okay, the two liquids are sitting here and sitting here. Now, I just mentioned to you that we're going to be looking, the basic model of an atom is we have a nucleus and then we have the electrons around the nucleus. Okay, specifically, they're going to be different energy levels, very specific energy levels, but all of them are going to have one layer on the outermost shell. Think of it as the layer of an onion, okay? An onion has multiple layers, but all the action, occurs in the outermost layer. When you cut that onion, you're cutting from the outside. Chemistry, that's what's happening. All the chemical reactions occur on the outside layer. That Roman numeral for the A elements will tell you how many electrons are in the outermost shell just by finding its position. So, for example, carbon is right there. Carbon has 6, its number is 6. We're going to learn that 6 represents the number of valence of total electrons. Okay, but of those 6, 4 of them are in the outermost shell. And the same is true for silicon. 4 of them, of its electrons total on the outermost shell, all the way down the road. And the same here, similar with boron. Boron, there's 3. And everybody down the road has 3 valence electrons. Way over here, on this column, is Roman numeral A. Everybody there has 1 valence electron. Everybody here has 2 valence electrons. Now let me ask you to make a prediction now. How many valence electrons would you say fluorine has right there, F? Based on what I just told you, what can you predict? Okay. Without even having to read the chapter or memorizing it. What we got there? We got 2 answers, exactly 7. Just by knowing its position. Oxygen has 6. And not just oxygen, but everybody in that group. Down here. And that's why within the group, they react very similar. Sodium reacts very similar as potassium, K, right below it. And they do that because both of them, though they have different number of electrons, both of them have 1 electron on the outermost shell. And that's what I explained earlier. That's where all the action occurs, on the outermost shell. Okay. And that's why fluorine and chlorine and bromine down group number 8 all react similar because they have the same number of electrons. Now, let me ask you a question. Have you deduced something here? I said earlier, let me clear this up a little bit. I got so much going on. I said earlier the driving force was to obtain the magical 8 electrons. Okay. We just stated here that fluorine has 7, whereas sodium only has 1 valence electron on the outermost shell. Now, from an energy perspective, would you anticipate fluorine to lose 7 electrons or gain 1? What does your intuition tell you from an energy perspective? Would it be easier? Maybe put it, me having 9 kids, is it easier to put 9 kids in the van or just put 1 in the van? Obviously, put 1, you got 7 kids roaming around, it's pretty difficult. Well, fluorine doesn't want to give up 7 electrons. Okay, it is very close to having the magical 8, so it's going to pick up 1. And sure enough, it does. In fact, everybody in that group is going to pick up 1 electron. And by picking up 1 electron, they end up with a negative charge. But more on that down the road. Where on the other side, sodium, from an energy perspective, it doesn't want to pick up 7. It's too much energy. It'd rather just give up 1. And when it gives up 1, the next energy level with electrons is the next one in, because the outermost one is empty now, and it obtained the magical 8. Okay. All right, so the ones in blue are solids, the ones in yellow are gases. Okay, and the purple, which is only 2, are the liquids. Okay, so be able to look at the periodic table and say, okay, element number 46, it's in solid. Okay, so on down the road. Now here's your diatomic elements. I stated earlier that there are 7. Okay, how to remember them? Here's a little something for you. Have no fear of ice cold beer. You don't like beer, call it beverage. H represents hydrogen, N represents nitrogen, F for fluorine, O for oxygen, I for iodine, C for chlorine, and C. A lot of people want to call this carbon. No. Okay, carbon is not a diatomic element. Okay, it's chlorine, and then B for bromine. Now, why do we want to know that? Because remember that reaction I showed earlier? We had sodium plus chlorine gave us sodium chlorine. You're going to get a lot of examples in assignments where you are given a chemical reaction in words. And from the words, you need to convert that to a chemical reaction. Like it could be, that reaction could be the reaction of sodium metal in the presence of chlorine yields sodium chloride. With that information, you write the chemical reaction. If you're using chlorine, INE, you got to remember that it's diatomic. Okay, so there's a difference. Chlorine versus chloride, which is part of the nomenclature, naming compounds. The INE is the element, the diatomic element, and it's true for bromine, it's true for all bromine, iodine, and so forth. Okay, fluorine. The chloride is the monatomic ion. That is chlorine that had 7 electrons and picked up 1, and now has a negative charge. That is the stuff, the chloride that you ingest, the sodium chloride. Okay, so there's a difference, and that naming will help you determine the formula for the ones that gain electrons, because we changed the name for those elements that gain electrons. We don't change the name for those elements that lose electrons. So you want to put this in long-term memory. With respect to metals, nonmetals, and semi-metals. Point number 1, metals always lose electrons. Nonmetals always gain electrons. So let's define what these things are. Okay. Well, nonmetals, how do we locate those? But on the periodic table, there's a little stair step. And let me pull up the periodic table right here. You see that over here? Right here, that little stair step. Well, on that stair step lists what are called semi-metals. Okay, now we have metals and non-metals. And then semi-metals, or another term that is used, is called metalloids. Now, what metalloids are those elements that have properties of metals and properties of non-metals. It is like a mule. Anybody know how to make a mule? Where the mules come from? Please don't tell me the mule store. A mule comes from a donkey and a horse. Okay, so the mule it's a hybrid. It has properties of a horse, properties of a donkey. Okay, and that's what a semi-metal is. Now we're going to work a lot with semi-metals. We're going to do most of our work in Chem 130 with metals and non-metals. Okay? So metal, and so that stair step, on the stair step are the metals. To the right of the stair step of the nonmetals, and to the left of the stair steps are the metals. Okay, with the exception of hydrogen. And let me show you this right there. And so here's that stair step starting with boron. We go diagonally and straight down, diagonally straight down, across, I should say, across, then down, and then across. Okay. 117, we predict that it's going to be a metalloid, not sure at this point. Okay, so problem is these numbers underneath there in parentheses, that indicates that they're reactive, and being reactive, they don't last very long, and then therefore it's difficult to study them and learn their properties. So the ones in red are pink, I guess, are the nonmetals, all the nonmetals here, okay? Including hydrogen, which happens to be in the far left. So don't think that hydrogen is a metal simply because it's over here with the rest of the metal. It is over there because it is in group 1A because it has one valence electron and one electron. So that's why it's very similar to lithium, sodium, and potassium, not because they're the same type of element, it's because they have the same number of valence electrons on a most shell. Okay, so again, at a glance, using a periodic table, someone says, okay, element number 112, is it a metal or a non-metal? You can say here that it is a metal. Furthermore, you can say that it is a solid at 25 degrees Celsius. Okay, without having to go and look up the properties of element number 112 or any of these elements. So basically on their, in their position in a product table, you can determine those physical properties. Now, notice something here. I remember I had this, my periodic table was labeled 1, 2, 3, 4, 5, 6, and 7. Okay. Now, I'm going to tell you something real quick, and then with that information, I want to ask you, you can deduce something. Those are different energy levels, okay? So you start off with the first energy level, okay? And that is where all the electrons are. And then you go to the next one, number 2, it's a bigger balloon. Number 3, bigger balloon, etc. So you got 7 energy levels, okay? Now, with that information, what do you predict is bigger? Who do you think is bigger with respect to the radius? Copper versus Ag, which is silver. Copper versus Ag. Who's the bigger element in size and diameter? What would you say? Any takers? I just told you that you have different energy levels, right? And if I look at copper, it's an energy level number 4. If I look at silver, it's an energy number 5. So who do you think is bigger, copper or silver? No takers? Silver, thank you. Exactly, it's in the bigger one. And the same token, if you needed to predict who's bigger, oxygen or sulfur, well, sulfur is bigger because it's in the 3rd energy level, more energy levels, okay? It's a bigger balloon, if you will, all right? And so when I compared this one versus hydrogen, definitely number 87 is much, much bigger than hydrogen, just simply by its position. Thank you, Ashley. That's good. I missed that. Lowercase g, you are correct there. Okay. All right. So that's one of the trends you can use to, figure out some properties about the elements without having to sit there and memorize all 118 elements and all their different properties. It's really unnecessary to do that. Okay. All right. Some of the properties of metals. Well, first of all, they're in general, they're very shiny. They get shiny appearance. Okay. They tend to be very malleable and ductile, meaning that they can be smashed very well. You can take a chunk of metal and flatten it and make it bigger. And it's like making tortillas in the ball, and you flatten it out, you got a big old tortilla. Or you can run it through some type of a die and go from one diameter to a much smaller diameter. When I was working in industry, I did a lot of work. We did a lot of work with quarter-inch copper, which came from Finland, which was ironic. Being born in Superior, Arizona, which is a copper mining town, I ended up doing most of my research on copper. So anyway, it would come from Finland because it's very specific properties. That's why it came here. And to make these quarter-inch plates and 7mm plates, they would take a big billet of copper, which is probably about 2 or 3 feet thick, and then roll it back and forth on these big plant and these humongous rollers. And they would take that and squish it all the way down through the quarter-inch. That's one of the properties of the metals. With the exception of mercury, all of them are solids. Okay, mercury's used to be used a lot for switches and thermostat. Okay, because they conduct electricity. Density, recall the density ratio of mass over volume tend to be high relative to other elements and compounds. They have a very high melting point, takes a high temperature to melt them. Think about the iron steel mills, their stuff is pretty hot. Okay, they're good conductors of electricity simply because on the surface, metals have a whole flood of electrons that go from point A to point B. Okay, get transferred. Actually, the electrons, it's been shown the electrons on a copper wire are not really going from. So if you want the electricity from a power plant, the electrons generated at a power plant are not the same electrons that you utilize to run your hair dryer. So what's happening is at the source and through the wire, the electrons actually go into areas that kick another electron out to go forward, like dominoes, if you will. And so eventually when you get to your home, you're using electricity, you're kicking the electrons from your wire, okay, because it just had a big cascade effect. Being good conductor of electricity, they're also good conductors of heat, okay. Nonmetals tend to have dull appearances, and the ones that are solids they're brittle solids. A lot of them are gases, okay, and their density is in general fairly low when compared to the metals, and they tend to melt at a much lower melting point temperature than metals, okay. Or conductors of electricity, therefore they're better insulators. So that's a little kind of a rule of thumb. If you're a good conductor of electricity, you're a good conductor of heat. If you're a bad conductor of electricity, then you're a better insulator. And that's why they put air in between panels of windows, because the heat doesn't conduct as readily. All right, so things to remember about this chapter is this: look at the periodic table and make sure you can get at least the name for the first 20 in those metals that we gave you, given the symbol. Okay, looking at the periodic table, determine any one of those elements, whether it's a solid, liquid, or gas. Okay, based on that slide number 35. Okay, also. Looking at this slide is looking at the element and determine whether it is a metal or a non-metal or a metalloid, okay, or semi-metal. Okay, we need to identify, the important part is we need to identify whether it's a metal or non-metal, because that is going to tell us what type of compound we are dealing with. For example, okay, if I look at sodium chloride, which is that table salt we showed you earlier, okay, sodium is a metal, okay, chloride is a nonmetal. Okay, so when we have a metal combined with a NM nonmetal, we have a very specific type of bond. We call that a ionic bond. Ionic bond. And with that in mind, that gives us a whole slew of different properties because it's an ionic bond. And we identify it to be an ionic bond because we identified the species that are put together, whether it's a metal or non-metal. When we look at things that have like H2O, guess what? That is a combination of non-metal hydrogen and non-metal oxygen. Okay, what that means is it has a very special type of bond. We call that covalent bond. And being covalent bonds, it has a very special character. Okay, totally different properties. Hydrogen's a non-metal, oxygen's a non-metal. Okay, what is happening between the two, the bond, the ionic bond, is more like two magnets coming together and attracting each other. There's nothing being shared. There's an attraction between the two because there is a full-fledged positive charge, and this will become clearer, which is related to the group it's in, has a plus charge for sodium, and the chloride has a full-fledged negative charge. And like positive and negative, they attract, and that's what happens. They come together. Compared to a covalent bond, it's not like that at all. The bonds are actually electrons that are being shared with each other. And my fingers represent the electrons. Electrons from one element, electrons from another element, they overlap a little bit and they form a bond and they share. They don't break apart, they share together. They can break apart, but it takes a lot of energy. The ionic bonds break apart fairly readily by just putting them in water. You got table salt, it dissolves the water, totally breaks apart. Okay, so it's important that we recognize who's the metal, who's the non-metal, because then that tells us what type of bond we have. And guess what? Of all the chemicals we deal with, there's only two types of bonds: ionic bonds and covalent bonds. That's it. Okay. No, nothing more. You would think there'd be a whole bunch of different bonds, but that's not the case. All right. That being said, guess what, folks? We are done with chapter 1. Okay. All right. Well, I tell you what, a bit early, but let's do this. Let's chapter 1 is done. We're going to jump into chapter 2. Let's take a quick short break, 15-minute break, a little bit early. And then when we come back, we will start up with chapter 2. Okay. So maybe I'll give you time to pull up the chapter 2 PDF file, kind of glance through it, or at least look through the overview of what we were going to talk about. We kind of introduced you about chemistry here. I gave you a lot of information. We're going to get a lot more of that in more detail down the road here, but we kind of introduced you to chemistry. And now we're going to have to shift gears a little bit and talk about mathematics. Okay, nothing complicated. And as I tell my students, if you can add, subtract, multiply, divide, and do some very, very simple algebra, that's all we're going to do. All right. So we're going to get into the mathematics a little bit. And then eventually chapter 3 talks about converting units from one unit to the other using a specific technique. And this is the technique that we're going to take and utilize this same technique with respect to chemical calculations down the road. Okay. All right. So let's take a quick 15 and then. Okay. I'm back. Oh, FYI, beside on my background, there's a list of chemicals and some of the flavors that you may ingest, like wintergreen and banana oil. It was pretty interesting that to make these compounds called esters, you combine what's called a organic acid and an alcohol, and you put them together, and you make these esters that smell very, very good. Singly, they don't smell too good. But once they're an ester, very nice. Anyway, any questions, comments? I'm going to jump into chapter 2. We definitely should have this done. Okay, so we're going to shift gears a little bit. We're going to talk about mathematics and numbers and accuracy, and what we call significant digits, significant figures. Now, the basic premise of this chapter, and this is true for any calculation that we do in this class from today on to the last day, is that when we do a calculation, okay, and the calculation comes from some numbers. Now we're going to do either we're going to multiply, subtract, or divide, add, subtract, multiply, divide. Okay, we're going to do that. Okay. And the point of all this is that the answer should not be more accurate than the least accurate number that you utilize to do whatever mathematical function you did. Okay. Does that make sense? You think about it for a second. Now, we all know that you can take a couple of numbers and put them in your calculator, and you end up with, 20 digits. And you might think in your head that, all right, I'm going to present the 20 digits because that's more accurate. But that is incorrect. Okay. Because if your measurement was done with an instrument that maybe can only go to the 10th of a decimal point in the accuracy of your measurement, then your answer should be no more accurate than a 10th of a decimal point, and not 40 decimal places. Okay? So that's the whole premise of this particular chapter. So there's practice problems on your modules. So make sure you get a chance to go over it. So what we have here is measurements. Okay, now we're going to be using mostly metric units. Okay, but the next chapter we're going to be talking about converting from English to metric units. And we do that because there's a technique that we want you to learn so you can utilize this technique when we start doing chemical calculations. Okay. The other aspect about measurements is that a number by itself has no meaning. So the statement, this book weighs 8, should tell you, well, your next question is 8 what? Tons, pounds, grams, milligrams? Exactly. So what is wrong with this comment is it's got to have some kind of a unit. Okay? Now, any measurement, and when we talk about measurements, we're talking about weight, mass, we're talking about volume, okay? And we're measuring the length. So mass, volume, and the length of something, okay? Everything has a degree of uncertainty, everything. Don't let anyone fool you and say that my measurement tool is 100% accurate. No, because even making that tool has a degree of uncertainty. Being in industry for many years, we had a plus or minus window that when we produce a product, it had to fit within plus or minus. Nothing ever hit dead on. Okay, nothing is exact. And so all measurements have a degree of uncertainty because it's governed by the accuracy of your instrument. Now, you know that if I get a ruler, I want to measure the length, and I got a ruler, and then when I measure a length using the ruler, and then I go back and measure another length, and this time I got a laser beam instrument. Obviously that laser beam is going to probably give me like more decimal places, to give me more accuracy than the measurement through the ruler, which would be even more accurate than if I just eyeball it and say, hey, that's about, I don't know, 20 feet. And then I get my ruler and I see it's more like 21.5 feet. And then I get my laser beam and I measure and it's more like 21.556 feet, okay? So. All right, so for lengths, what we use unit-wise are the symbols given there. Lowercase c and m for centimeters. I might have a whole chapter about the metric system, not a whole chapter, a whole PowerPoint slide, which is also on your module number 3. I uploaded that yesterday. It deals with the metric system, okay? So we use cm for centimeter, mm for millimeter, m for meter, and km for kilometer or kilometer, okay? Now, obviously, you're familiar with this. As I was explaining and doing the measurement, either eyeballing or using laser beam, the tool that we utilize has uncertainty. But you can see, hopefully, that the white ruler is least accurate than the brown one here, okay? Simply because the brown one has more increments that we can make a better guess. Basically, any measurement is a guess. And the more accurate tool that you have, it's just a better guess, okay? Now, if I were to say measure this instrument here, using these two rulers, and I wanted to, they both start at 0. And let's say I wanted to measure that distance from 0 to that line. Okay. All right. Using the white ruler, what is your best guess for that length there? Using the white ruler, what would you say, guys? What's your best guess there? Mark, can we all agree that it's 5 something, right? Yeah, 5.6. Yeah, that'd be very, very good. 5.6 for the white ruler. Okay. And so what that tells you, using a white ruler, you can only be as accurate as to the 10th decimal place. Okay. Because that's the best you can do, given the ruler that you have. Now, what about using the brown ruler? What could you say the measurement would be there? Obviously a 5, right? Okay. But we agree with 5.6, like the white ruler. But can we not go one more decimal place? What would you say, using the brown ruler? What would be the number? Best number. 5.65? Yeah, that's fine. See? Yeah, some people would look at that and say, okay, maybe it's 5.64. And that would not be incorrect. Or some people would say 5.66. Okay, that's your best guess based on how you read that instrument. But the point is, using the brown ruler, we can go to the 100th place in our decimal, whereas the white ruler, the best we can do is the 10th place. So obviously the brown ruler is more accurate. Now, if we were to take these measurements, this 5.6, and do some calculation with the 5.6, well, our answer, as far as how many digits we put in our answer, will be governed by the number of digits, what we call significant digits of 5.6. We could not be, very much more accurate than what is governed by the white ruler. So it's all about how accurate your measurement tool is. Okay. Now, for some reasons, that example I just did, using the white ruler, students have taken it to the 100th place, but it's really very difficult to do that because you don't have enough increments in between the digits to even do a best guess to the 100th place using the white ruler. You can with the brown one because there's more increments in between. Okay. All right. So the one that has more uncertainty here is the white one. With mass, we use the units mg, lowercase mg for milligrams, kg for kilograms, and then g is the most common unit for mass, which is grams. We have two different types of instruments here that kind of give you an idea of what can be used out here. On the balance on the right, the digital balance, very accurate compares to the balance on the left. If you look at the number on that on the right side, it goes to 18.7954. You can go up to 4 decimal places there. So obviously, the digital balance is a lot more accurate than the one on the left. The one on the left, you got to use counterbalances, and you might be accurate to maybe hundredths of a place. It's hundredths of a gram compared to the digital. So, okay, mass and weight. There is a difference between mass and weight. Weight is defined as the mass times the gravitational constant here on Earth, which is like 9.8 meters per second squared. Okay, and you end up with different units. But anyway, the point is this, that there is a difference between weight and mass given by this equation. But since we're here on Earth, you'll find that the terms are interchanged. You know, your mass and weight, if you see a question that says, what is the weight? Well, they're talking about mass. If the question says, give the mass, well, you're talking about the weight, okay? We interchange the terms, though they are separate things, okay? For example, an astronaut here on Earth weighs about 170 pounds, but on the moon, we're looking at 29 or so pounds, simply because the gravitational force, that constant on the moon, is a lot different than here on Earth. Okay, with respect to volume, well, the units that we utilize for volume are in metric units, or capital L for liters. And we also use the prefixes of K for kiloliters, M for centiliters, and we have some other ones, deciliters and so forth, but I'll show you that here in a bit. On the right-hand side, you have instruments utilized to measure volume. A note about this, because you'll see that in the labs, that you want you to take a measurement. Let's say you're going to use this instrument here. This is called the graduated cylinder. The 0 point is down here in the bottom, okay? And so then the scale goes up. And so when you measure a volume, make sure you know where the 0 point is and you are using the correct number. You know, let's say this is 20 and your mark is right here. So you're over 20, and not treat this as, say, going the opposite direction, going 19 maybe. Okay, just make sure you know which direction, where the 0 point is. So you read the right scale. Some instruments, the 0, like this one, this is called a burette. And this instrument you clamp on, and you are dispensing a liquid, and fairly accurate liquid. But this one here, the 0 point is on top, and you read it from top to bottom. So you open the stopcock here, and you let liquid out, and then you do a measurement. Okay, you do a reading. Okay. Some of the units, I'm sure maybe some of you are familiar with the unit CC, which really is nothing more than stands for cubic centimeter. This is 1 centimeter by times 1 centimeter times 1 centimeter. Now the factor here is the units of milliliters, which is the volume in metric units, is milliliter. So 1 milliliter is equal to 1 cc, or 1 cubic centimeter. This is a conversion factor, this ratio. We can write that, and more in this down the road, trust me. We can write this factor with millimeters on top, or we can write it with centimeters on top in the numerator. Okay, which one we select depends what we multiply this factor by. Because if we multiply the factor on the left, we are multiplying it with, say, for example, cubic centimeters. Because we want to convert 10 cubic centimeters to milliliters, and the units, the centimeters cancel out, okay? If on the other hand, I have units of 10 millimeters and I want to convert that to centimeters, I use a factor on the right. Okay, because my millimeters cancel out, leaving me with the units of centimeters. It's all about keeping track of your units, okay, and using these conversion factors and putting it into a ratio. Right, here's one, for example, for English units that may help, because I've always had trouble when I got to English units and, you know, how many quarts in a gallon and how many pints in a cup and so on and so forth, but this kind of helps out. You have access to this. It's a PDF file. Again, it's in module 3. But if you look at this, you have the big G on the outside, right? Big G on the outside, which represents a gallon. So there's 1 gallon. And inside the gallon, there are 4 Qs, okay, which represent 4 quarts. So there are, in 1 gallon, there are 4 quarts. Now, if you look within 1 Q, there are 2 letter P. So that tells you that there in 1 quart, that is equal to 2 P for pints. Okay, we're talking the English units here. And carefully look within 1 P, where you got 1 pint. Well, that is equal to 2 C's, which is 2 cups. 2 cups, okay? And all these 3 units, again, are conversion factors that I can utilize. So I can write them with 1 gallon over 4 quarts, okay? And I will use this factor if I'm multiplying this factor by quarts. Maybe I got 10 quarts, I need to convert to gallons. So I multiply it with this factor, and notice that my quarts cancel. Or I can invert that and put the quarts, 4 quarts on top and the gallons in the bottom. And I will use this factor if I got, say, 10 gallons, and I want to convert that to quarts. So notice my gallons cancel, leaving me with units of quarts. So this is where the basic algebra comes into play. You know, you might want to refresh your basic algebra to make sure you set that up to make sure that the units cancel out properly, okay? Also, the other aspect is this. I know you might be tempted to take that 1/4 and convert it to 0.25. So 0.25 gallons per quart. And that's fine if you keep it consistent and you understand that, because I've seen where people have done that in the past and do it because down the road we can have at least 3 or 4 conversion factors, okay? And if you start doing the inversion and converting that the numbers, you might run into problems. So my suggestion is just leave it alone, leave it 1/4. And just, if you invert it, invert the whole thing before 1. Don't worry about it, 0.25 and so forth. That way there's no question, no ambiguity. You got it. You got this problem set up properly. And we're going to talk at length about that, because once I set that up, it's just a matter of keeping track of my units and making sure units cancel out like I've been showing here. And you end up with the final units that you're looking for. And the problem is set up properly. And if you follow that technique, I guarantee you 99% that you will be set up properly. I can't give you 100% because you control the calculator and I can't control the numbers that you punch in there. Okay. But follow this format and we'll do more in detail here when we get to the calculations of chemical reactions. It will hopefully make more sense. I will, for example, give you an example of using this technique using the very extreme, crazy conditions where I'm literally going from apples to oranges. Okay. And I can do that as long as I have conversion factors. All right. We were talking about measuring in volumes earlier. And there's one thing about measuring volumes is most liquids in the cylinder form what is called a meniscus. It's like a concave shape. The question is, well, how do I read that? Well, you imagine this is your eye over here, okay, and you look in that direction, and you look at the bottom of the meniscus, okay? The bottom of the meniscus, and that is where you make your reading on the scale. Okay, so this one here is probably about 21.5 milliliters. Would you guys agree? 21.5-ish? Not bad. You know, if you say 0.6, you would not be incorrect. You know, because that last number, again, is a degree of uncertainty. And we're not sure if that number is 0.6 or is it 0.4. All right. Which brings us to what is called significant digits. Now, the important aspect is this. When we say the term, and I wish there was a different way to use a different word than significant, because using the term significant, it kind of gives a connotation of that that number does not worth anything. Well, yes, it is worth something, okay, but it's not worth anything when we determine how many what are called significant digits we have in our answer. Okay. Earlier I said to you that I can do a calculation and my calculator can spit out 10, 15 digits, right? And you might be tempted to present that as an answer, 10, 15 digits, but that would be incorrect because you weren't that accurate in the measurements. And so to determine how many digits to present your data, we have to talk about significant digits, whether they are significant with respect to determining how many final digits we have in our answer, okay? All right, so we'll give you, and then we got a whole series of rules, and then what I'm gonna do is take those rules and shorten them up and just give you a simple question to ask yourself when it comes to zeros. Why? Because the integers are always significant, but the zeros can be ambiguous a little bit. All right, so all digits in the measurement are known plus one or more, and it's estimated. The last part is an estimate, okay? And using those scales, here we use the example of a surgical scale and a bathroom scale. Obviously, the surgical scale has more accuracy and therefore has more significant figures in their number, okay? The same is true here. This is like we did earlier, where the top one, we can only go to the 10th place. So, you know, best guess, would you say, I don't know, call it 29.2? Would you agree on that being the case? Yeah, okay, that's not bad. And down here being 29, definitely 0.2, maybe 5. Okay, and so obviously here we got 2 decimal places versus 1. And so we have more significant digits with the bottom one simply because we use a more accurate measuring tool. Okay, so how do we determine the digits, the numbers, whether they are considered significant or not? Well, rule number 1, that all integers, numbers 1 through 9, always count. So the number 4895.2 has 5 significant figures, 5 sig figs, okay? Leading zeros, numbers less than 1. And leading zeros are not counted as significant. They're just holding the decimal place, okay? And so these zeros, like 0.000, are not considered significant in determining how many significant figures you need for your answer. They are significant with respect to magnitude. Okay, so we don't lose that. We're just determining how many sig figs for your answer. So we got 5, 4, 5, 4, and those are integers as per rule 1. So this number has 4 sig figs, okay? And to give you a heads up here, if we were going to multiply these two numbers with 5 and 4 sig figs, our answer, if we're going to multiply and divide, our answer should carry no more than 4 sig figs. Okay, because this number in the bottom, number 4 sig figs, is the least accurate digit. Captive zeros, these are numbers between integers. They are considered significant and therefore count. So the number 3015 has 3 sig figs. The 3, the 0, and 5 are count as significant. And the last 0, though it's significant with respect to magnitude and value, it doesn't count with respect to sig figs. Okay. The next example is 0.002001. Well, the first 3 zeros are leading zeros as per rule number 1, 2. And then the numbers between the 2 and the 1 are captive as per rule number 3. And they are considered significant for that number. So that number has 4 sig figs. Okay. Trailing zeros. If you have trailing zeros, that's numbers after an integer, and there is a decimal point anywhere on that number, they're considered significant. Okay. And those are the 2 questions you got to ask yourself when it comes to zeros. All right. So here we look at this 0 here. There's an integer in front of that 0, and there's a decimal point in that number. Therefore, that 0 counts. The 8s are integers, so this number has 3 sig figs. Okay. The first 2 zeros, ask the question there. Ask the same question for the leading zeros. If you forgot rule number 2, but just ask the question for the leading zeros. Is there an integer in front of these 2 zeros? Answer is no. Okay. And since you got to know, then these 2 front zeros don't count as being significant. When you ask the same question for this 0, you get, is there an integer in front of that 0? You get a yes. Is there a decimal point anywhere in that 0? You get a yes. That means when I get 2 yeses, then those zeros are significant. If I get a no in any one of the questions, be it a decimal place or an integer in front of the 0, then those zeros don't count. Okay. I think that kind of simplifies it with respect to the zeros, because the zeros are the ones that maybe sometimes cause the most confusion. Okay. Now, adding decimal places makes all the zeros significant. So, for example, if I had a number like 200, okay, I have 2 sig figs. Or 2, excuse me, what am I saying? 1 sig fig. Or, you clear this up a little better. The number I have is 200. I have 1 SF, one significant figure. Okay, from 200. Because again, for the zeros, is there an integer in front of the zeros? Yes. Is there a decimal point anywhere in the number? No. So those 2 zeros don't count as being significant. Okay. Now, if I take that same 200 and I add 0.0, guess what? Now I have 4 sig figs. Okay. So if I look at these zeros after the 2, ask the question for those zeros, is there an integer in front of those 3 zeros? The answer is yes. Is there a decimal point anywhere in that number? Answer is yes. Therefore, all those zeros count as significant. Now, what can happen sometimes is you could be asked a question. I have 2 numbers here, 200, and the other number is 200.0. Is there a difference between those 2 numbers? What would you guys say? Is there a difference between 200 right here and a difference between 200.0? Yeah, you see, we got a couple answers. No difference. You are correct with respect to value, because let's say I put a dollar bill symbol in front. Yeah, they're both $200, right? But there still is a difference with respect to accuracy. Okay, the 200 is the least accurate than the 200.0. Because the 200.0 can go to the 10th place. Okay, and so the 200, its true value, because that last number, there's always a degree of uncertainty. Its number can be a range of 201, 200, and 199. You know, that could be where the true value sits someplace, you know, because of the degree of uncertainty. Whereas the one with the 10th place, its true value can be 200.1 down to 199.9. So notice the range is much smaller, it's a lot more accurate. So yes, they're not different, 200 and 200.0, but they differ in respect to accuracy. Okay. Now we also have any measurement. The takeaway here so far is this: any measurement has a degree of uncertainty, so therefore could play a factor in determining the number of significant figures in your answer. Exact numbers do not play a factor in it because they are exact numbers. When you count the number of people, like 14 here, there's exactly 14 people. Some conversion factors have exact numbers, like 3 feet per yard. Is exactly 3 feet. It's not 3.1. It's not 2.9. It's exactly 3 feet. Just like there are exactly 100 pennies in a dollar, or any quantity, 5 iPads or a 12-pack. It's exactly 12 cans of beer or whatever you're going to buy soda from. All right, those are exact numbers. So all exact numbers do not play a factor with respect to determining how many sig figs you have. Anything that's measurement, however, measured is not exact, because there's a degree of uncertainty, because the tool that you have can determine how accurate you make that measurement. So 7 inches is a measurement. Okay, 200 pounds, again, is a measurement. And don't be fooled by anybody telling you that, yeah, it's 200 pounds exactly. Well, no, because there's a degree of inaccuracy in that measurement, 10 ounces. So any measurement has a degree of inaccuracy, uncertainty, and therefore could play a role in determining how many significant figures you have in your answer. Okay. All right, so for example, let's take a look at this number here. We got 5.05. Okay, who can tell me how many sig figs are in that first number? 5.05. How many significant figures are in that number?
3.
You got 3? That is correct. All right. How about 1200? 12,1200. How many sig figs do we have here?
2.
2. And that is also correct. All right. And what about 0.02020? A little bit more.
4.
4. We got a
3.
You got 4 or 3. Okay. Anybody else? Anybody else want to take a poke at it? We got 5. Okay. So we got 3, 4, and 5. Okay. Let's break it down. Best way to attack any problem is you break it down in steps. And remember the questions you have. Is there an integer in front of it? And there's a decimal. Let's take a look at the first 2 zeros. Okay. Ask the question, is there an integer in front of those 2 zeros? No. So they do not count as significant. Okay. All right. So let's take a look at the second 0 between 2. Okay. Now you can refresh your memory and say, okay, that's a captive 0, so it would count. But let's say you forgot. Ask the same questions just for that 0. Is there an integer in front of that 0? Yes, there's a 2. is there a decimal point anywhere in that number? And that's a yes. So that means that zero is considered significant. All right. We know that the twos are integers are going to count. So right now we got 3 sig figs, which leaves the last one there. And ask the same question again. Is there an integer in front of that last zero? Yes. And is there a decimal point anywhere in that number? And the answer is yes. So that last zero also has yes answers. Therefore, we have 4 sig figs. Okay. 4 sig figs. What about the next one? 0.0005. What do you guys think?
One.
1, exactly. Because again, those zeros up front are leading zeros, but then if you forget, ask the questions. And there's no integer in front of those leading zeros, so that you got to know automatically. All right,
Wait,
what? Yeah,
I'm
go-
sorry, on the problem number 3, the 0, what kind of 0 is the one that's on the very, very end?
This one right there,
Yeah,
that is considered significant. I
no,
don't
because I'm
understand.
saying there's like leading 0, captive 0, trailing, like
Ending zero.
ending 0, okay.
Yeah, at the end, trailing zero, I think the rule called it.
Oh, trailing 0.
Yeah, it's a
Okay.
trailing zero. If there's a decimal point in that number, because 50 also has a trailing zero. So how many sig figs does 50 have?
2?
No. Okay, ask the question. It's a trailing zero, that's correct, but is there an integer in front of that zero? Yes, there's a 5. Now ask the second question. Is there a decimal point anywhere in 50?
So it has to have a decimal to be the trailing?
No, yeah, that's correct. That's correct. You gotta have a decimal point. Let me correct you a little bit.
Okay,
It is a trailing zero, but there must be a decimal point for that zero to be counted as being a significant figure. Okay, does that make sense?
yes.
Okay, compared to the next one,
Mhm.
which would have how many sig figs?
Just 1,
No,
2,
no.
3.
I got a 3. Okay, nope. Don't guess, nobody guess. Think about it, break it down stepwise. If the
So it's
first,
4 then?
yes, 4,
Oh,
exactly.
yeah, because the zeros count, and then that means the 0 before that counts, because the ones after it count.
Exactly, for all those 3 zeros, there is an integer in front of it, and for all 3 zeros, there is a decimal point in front of it. Therefore, you have 4 sig figs. And then the 1, 2, 3.45, they're all integers, so they automatically count with respect to being counted as significant. All right, and finally, 8,090. Okay. What, how many sig figs would I have here, guys? You got a 3? Somebody say 3? 3 is correct. Okay. Because first of all, the 0 between the 8 and the 9 is a captive 0, and all captive zeros, regardless of decimal point or no decimal point, always count. Okay, the last 0, which is a trailing 0, but is not significant because there's no decimal point in there. And if there were a decimal point in that number, then that last number after 9 would count. Okay, so once we determine the sig figs, what does that mean to us? That means this, that if we're going to do, and I mean mathematically, what I'm talking about right now, when we're going to multiply, come on, pen, multiply or divide, we look at significant figures. If I were going to take these two numbers and I was going to multiply them, okay, then my answer should not have more than 2 sig figs. Because that number is the least accurate when I compare the two numbers. If I'm going to do either multiply or divide, let's say these two numbers, okay, my answer should have no more than 1 sig fig, because that number is the least accurate number. Okay, you follow how these 50 and 50.00, how 50 is the least accurate? Because the 50 doesn't have, it could be, anywhere from 49 to 51, the true value. The 50.00, that is accurate to the 100th place. And so if I'm going to do any type of multiplication or division between these two numbers, my answer cannot have more than 1 significant digit. Remember, your answer cannot be more accurate than the least accurate digit that you used. That's the whole point here. I've had answers presented where they typed it in the calculator and they gave me like 10 digits. Which by itself, sounds pretty cool. You got 10 digits, but very few instruments can be that accurate. All right, so that's the whole point of this exercise. This flow chart kind of goes over the questions I state, ask the question whether it's going to be significant or not. And then again, we're only talking about zeros because those are the ones that can be ambiguous at times. The integers always count. Numbers 1 through 9. It's the zeros where sometimes they get a little confusing, but if you ask, unless they're captive, when they're captive, they always count. But any other time you can ask the question, is there an integer in front of them? And is there a decimal point anywhere in that number? If you answer yes, then those zeros are considered significant. Okay. Now, once we determine that, you might say, okay, you got this 15-digit number. Well, how do I truncate it? How do I bring it down to the correct number of significant figures? Well, we're going to talk about rounding. We're going to round that number. The point about rounding is we're going to look at the number that we need to round, and one or two things are going to happen. That number stays the same value, or it gets pushed up to the next one. Okay, it doesn't drop from whatever the number is. If it's a 5, it's going to stay a 5 or go up to 6, but it's not going to go to 4. Okay, and that is going to be governed by its immediate neighbor. We don't care about what is happening 10 digits down the road, nor do we care that, okay, I got a 9 here. If I round that becomes an 8. Next number becomes a 9, or so on. No, only the immediate neighbor, and that's it. All right. And we use the rule of greater than or equal to 5. If the immediate neighbor is less than 5, then that number in question remains the same. And the example here we have 5.4. We've been asked to round it up to 1 digit, okay, which is the 1 digit, which is the 5. Okay, we look at the immediate neighbor, okay, which is the 4. It follows rule number 1, and therefore that 5 remains a 5. Okay, now here's the thing that sometimes students forget. Sometimes what students do is they take that 0.4 and they make it into a 0. And what have you done if you convert that 4 to 0 to your number here? How many digits, sig fig digits, do I have at 5.0? Don't I have 2? The question was to round it up to 1 digit, to 1. Okay, so you have to drop any number after the decimal point to 0. Okay, but any number before the decimal point, you don't drop, you convert that to 0. Otherwise, you change the magnitude. Okay, and more on that here in a second. So if you look again at the neighbor, and the neighbor is either equal to or greater to 5, then that number in question gets kicked up to the next value. So the example here is 5.5. The neighbor is 5. It follows the rule number 2. So the number 5 gets converted to 6, okay? Not 6.0, but 6. Now, we don't change the magnitude. And what do we mean by the magnitude? Well, for example, down at the bottom, it says, first of all, when you're asked to round a number at, look at the value of the number that you're at. For example, they want you to round to 1 sig fig, 5,400, okay? So they wanted to round 5,400 to 1 sig fig, okay? Well, find the 1 sig fig position, which happens to be the first guy, first number, okay? Look at the neighbor, follow the rounding rules. It is less than 5, so that 4, that 5 stays at 5, and that 4 gets dropped to 0, okay? And so that is our number rounded to 1, our number 5,400 rounded to 1 digit, 1 sig fig. We don't drop to 0 because we end up with 5. And you have changed the magnitude. Keep track of the magnitude. One way to look at this is, put a dollar bill, a symbol in front of it. Okay, I'm at the $5,000 range, and I'm going to round it to the $5,000 range, not the $5 range. It's quite a difference, right? Factor of 1,000. So that's what we mean by don't change the magnitude. And so numbers before the decimal point get converted to 0. Numbers after the decimal point just completely get dropped. Okay. So don't drop the numbers before the decimal point. All right, here's an example of taking numbers, and this could be an example where you've done some mathematical function, and based on the mathematical function you did, that your answer should have no more than 3 sig figs. So there's your answer in the calculator, 1.8374. So now I want to put it, excuse me, I want to write it with 3 sig figs. Starting from left to right, you find the 3 sig fig position, okay, which is the number 3 there, okay? Now you look to the immediate neighbor, which is a 7. Follow the rounding rules. 7 is greater than 5, which means that 3 gets bumped up to 4. Okay, so your answer that you present would be 1.84. And again, that is governed by the numbers you either measured and did the mathematical function to get you to this answer. It will be incorrect to write 1.84 to present 1.8374 as your answer, because you were not accurate in your measurements to the 4th decimal point, okay? All right, let's take another number here. This is 7,162.32. All right, I want you to round it to 3 sig figs. So starting from the far left, move over 3 positions to the 3 sig fig position, which is the number 6. Look at the immediate neighbor, which is a 2, which tells you the 6 stays as 6. Now, the 2 gets converted to 0, and the 0.32 gets dropped. Okay? Because if you drop the 2, now you are at 716, which is a factor of 10 away of your original value, your magnitude. The original number was 7,000. You're in the 7,000 range, not the 700. Okay, so be careful about that. Numbers before the decimal point and after the decimal point. Right now, you might say, well, what if I change my 3.2 to 0? So what if I did this and I go 7160.00? What have I done here if I take the 3 and 2 and convert to zeros? Okay, how many sig figs does this number have? 7160.00. How many sig figs? Anybody know? That's 6. It says 6 figs, which is counter to what the problem was to bring it to only 3 sig figs. So by making these numbers after the decimal point to zeros, you have done nothing to present your number in the correct number of significant digits. All right, let's take a look at this one. 0.00, those are leading zeros. So we look for the 3 sig fig position, which is the 1. Check out the neighbor. The neighbor is 1, which means the first number 1, remains the same. So our answer is 0.00131 millimeters. Okay, don't forget your units. 24,925, like we've been doing from left to right, determine the 3 sig fig position. Look at the immediate neighbor, which is the 2, which tells you that the 9 remains 9, and the 2 and the 5, which are numbers before the decimal point, get converted to 0. Okay, because we're in the 24,000 magnitude range. Okay, not the 249 range if we drop the zeros. That's where it puts us. Okay, so key points, drop numbers after the decimal point when you're rounding, and numbers before the decimal point get replaced with zeros. Okay. Now that we're trying to figure it out significant digits, here's the thing. We're going to talk about adding and subtracting digits. Now, when we add and subtract digits, I want you to think about decimal places, not significant figures, okay? Because if we look at decimal places, that tells us the accuracy. We're not doing anything different. We're still dealing with the accuracy of the numbers you do your mathematical function. It just, for adding and subtracting, we determine that slightly different than we do when we multiply and divide. And so we look at these two numbers here, 13.5478, and we're going to subtract 11.20. And it could be add 11.20. Now, which of these two numbers is the least accurate? Now, who can tell me that? Which number is the least accurate? The 13 or the 11? The 11.2, that is correct. It is the least accurate, and it has 2 decimal places. So therefore, our answer should have no more than 2 decimal places, okay? So when you present it with this, do the math of all the digits. Don't truncate anything. Don't round anything before. Do all the math. And when you subtract, you get 2.3478, okay? And because you have 2 decimal places for 11.20, where you're going to truncate and get rid of everything will be at the 4 position, number 4. So you do your rounding rules like you normally would. Nothing new here. Look at the neighbor. Neighbor is a 7, okay, which is greater than 5. So that 4 becomes a 5. So your answer, your presented answer is 2.35 feet, okay, which has the same number of decimal places than that number that you utilize with the least number of decimal places, okay, because 11.20 is the least accurate. Again, it will be incorrect to present all of this as your answer, because if both numbers are accurate to 4 decimal places, then yeah, that'd be okay. But one of the measurements here only went to the 2 decimal places. It would be analogous to, maybe the 13.5478, maybe you use a laser beam instrument to get that 4th decimal number. Whereas 11.20, maybe you use that brown ruler that we had, okay? So the brown ruler is going to be less accurate. So our answer can't be more accurate than the brown ruler. Okay, so takeaway here, big takeaway, and don't mix and match, okay? So if you have a problem, they ask you a question and they say, give your answer with the correct significant figures. The first thing you should need to stop and think is this: what am I doing mathematically? Look at the problem. If I'm doing adding and subtracting, focus on decimal places, okay, to give me the correct number. Because adding and subtracting have nothing to do with sig figs. Okay, how many sig figs are in 2.35? You can tell me that. Exactly, it's 3. How many sig figs in 13.5? So there are 3 sig figs there. How many sig figs in 13.5478? $13.5478. Aren't they all integers, right? 6, exactly. So we got 6 sig figs. And then finally, how many sig figs do we have at 11.20? We got 4. And I'm trying to demonstrate here that not when you add and subtract, don't think about sig figs, think about decimal places, because sig figs don't play a role in adding and subtracting. Decimal places play a role in adding and subtracting. We got 6 here in my 2 problems that I'm working, but our answer has 3 sig figs, but it has 2 decimal places, which is consistent with the 2 decimal places of my least accurate number. Okay, note the difference. This is just a reminder as to the decimal places, the tens place, 100 place, etc. Okay, now when we come to multiplication, multiplication deals with sig figs. Now you deal with sig figs, okay? And your answer should have the same number of sig figs as the digit with the least number of sig figs. Look at these 2 numbers, 3.546, okay? Meters times 1.4 meters. 1.4 has 2 sig figs. So our answer should contain no more than 2 sig figs. Okay. So notice here, 2 sig figs, 4 sig figs. Okay. And so we do the math. We don't truncate anything. We do the math with all the numbers. And then we go to the 2 sig fig position, because that is the least number of sig figs our answer should be. And we do the rounding like we've been doing. So we look at the neighbor. Neighbor 6, the rule says kick the 9 up to 10, carry the 1. So our answer is 5.0, okay? Which has the same degree of accuracy as the one with the least number of significant figures. And don't forget our units here, because we're multiplying. So m times m is meter squared, okay? And so when it comes to multiplication and division, focus on significant figures. Don't mix and match, okay? And I understand that a lot of the questions says present your answers with the correct number of sig figs. Well, when that occurs, when you read that, the next question you ask yourself, what am I doing mathematically? If I'm adding and subtracting, then I work with decimal places. If I am multiplying and dividing, then I work with sig figs, okay? All right, which brings us to scientific notation, which, you know what? I didn't realize you got 355. Think I will stop it here. Definitely gonna move the exam to the following Saturday. Okay, because we still need, we got about 10 more of these, 8 more slides, which won't take very long. And then we'll do chapter number 3 next Friday. We'll definitely finish that one, a little bit shorter. So when I stop it here, I got 3:56.